Continual graph learning, CGL, is a challenging task that aims to extend static graph neural networks, GNNs, to dynamic task flow scenarios. Experience replay, methods, inspired by the complementary learning systems theory, have achieved state-of-the-art performance in CGL. However, existing methods focus on identifying samples by feature significance or topological relevance, which limits their utilization of comprehensive graph data. To bridge this gap, the proposed method, Feature-Topology Fusion-Based Experience Replay, FTF-ER, integrates information from both feature and topological levels to mitigate the catastrophic forgetting issue in CGL. FTF-ER employs two theoretically grounded approaches to calculate node importance scores: gradient norm score, GRAND, for feature-level importance, and Hodge Potential Score, HPS, for topological level importance. HPS, a novel module, calculates the topological importance of nodes using Hodge decomposition on graphs, HDG, providing more accurate global topological information compared to neighbor sampling. By pre-computing HPS before training, FTF-ER efficiently captures comprehensive global topological information in the node sampling phase, eliminating the need for additional nodes during subgraph creation. The FTF-ER workflow involves selecting nodes from each class based on importance scores to create induced subgraphs for the buffer. This enables the model to maintain classification performance across tasks, i.e., continual learning. Experimental results on 4 mainstream graph datasets demonstrate that FTF-ER achieves state-of-the-art performance in the class-incremental learning setting, with a significant improvement of 3.6% in accuracy and 7.1% in F1 score on the OGB-Arxiv dataset. The proposed method addresses the limitations of existing methods, which focus on either feature or topological information, and neglects global topological information. FTF-ER provides a novel and effective approach to continual graph learning, leveraging both feature and topological information to mitigate catastrophic forgetting. The proposed method, FTF-ER, addresses the catastrophic forgetting problem in continual graph learning by leveraging both feature and topological information of nodes. Unlike previous methods that select samples based on either feature significance or topological relevance, FTF-ER combines both aspects to provide a comprehensive utilization of graph data. The paper first introduces the concept of Hodge decomposition, which has been applied in various fields, including machine learning, robotics, and image processing. Hodge decomposition is used to obtain global topological information without introducing extra nodes, reducing the buffer storage overhead of topology-based experience replay methods. The problem definition and notations for continual graph learning are provided, including the node classification problem, graph structure, and task settings. The paper focuses on the class-incremental learning setting, which is considered more challenging due to the larger classification dimension and absence of explicit task boundaries. The experience replay method is extended to the subgraph level, where a rational experience sample selection strategy is crucial. The traditional experience replay method preserves a small number of training samples from past tasks and replays them during subsequent tasks training to retain the model's classification ability for past tasks. The key to experience replay methods lies in designing a rational experience sample selection strategy. The paper proposes a novel node importance score calculation process, which integrates feature information and topological information. The gradient norm score is used to compute the importance of nodes in the feature space, while the Hodge Potential Score is introduced to calculate the importance scores of nodes at the topological level using Hodge decomposition. The two importance scores are then integrated into a weighted average score for node selection. The complete pipeline of the proposed method is illustrated, including the calculation of node importance scores, experience sample selection, and the auxiliary loss function for continual graph learning. The paper aims to tackle the more challenging class-incremental learning tasks to showcase the effectiveness of the proposed method. In this paper, the authors propose a novel feature-topology fusion-based experience replay, FTF-ER, method for continual graph learning, CGL. The primary goal of CGL is to learn a model that can continually adapt to new tasks without forgetting previous ones. The FTF-ER method leverages both local and global topological information to select the most valuable nodes from the complete training dataset for efficient graph learning. The authors introduce a new Hodge Potential Score, HPS, to measure the global topological importance of nodes, which can achieve more accurate global topological information compared to other topology-based methods. By applying HPS, the storage overhead during model execution is significantly reduced. The authors also present a fusion strategy that combines HPS with GRAND, a local node importance scoring function, to leverage comprehensive graph data. Experimental results on 4 public datasets show that the proposed FTF-ER method outperforms current state-of-the-art methods in the CGL field and performs similarly to the joint training method. This indicates that the FTF sampling strategy effectively selects the most valuable nodes from the complete training dataset. Further analysis reveals that the FTF-ER method significantly outperforms other CGL methods under the class-IL setting, with improvements in both average accuracy and average forgetting. The proposed feature-topology fusion-based experience replay method, FTF-ER, addresses the catastrophic forgetting issue in continual graph learning, CGL, by fusing feature-level and topological-level information. The method leverages Hodge decomposition on graphs to calculate the topological importance of nodes without additional storage space, obtaining more accurate global topological information compared to local neighbor sampling. Experimental results on 4 datasets under the class-IL setting demonstrate that FTF-ER outperforms state-of-the-art methods, including fine-tune, EWC, LWF, MOS, GEM, GNN, TWP, and SSM. The method achieves performance close to the upper bound throughout the entire learning process on all 4 datasets, as shown in Figure 4. Ablation studies in Table 3 and Table 4 demonstrate the effectiveness of the proposed node sampling method, which integrates feature-level and topological-level information. The results also show that the fusion of feature-level information and topological-level information surpasses the approach of using only one of these types of information. Furthermore, the performance of FTF-ER, HPS only, is superior to that of FTF-ER, GRAND plus HPS, on the AF, while it is inferior on the AH, suggesting that topological information is more effective in enhancing the model's memorization ability on the OGB-Arxiv dataset. In terms of computational overhead, FTF-ER has nearly the same buffer memory overhead as GNN and significantly lower than the SSM and GEM methods. The method also achieves the best overall training time among all ERBASED-CGL methods, mainly attributed to treating topological importance calculation as a preprocessing step. Figure 5 visualizes the performance matrix of average accuracy, demonstrating the effectiveness of FTF-ER in alleviating catastrophic forgetting issues of CGL. The results show that the colors of most tasks stay pretty much the same, matching the smooth curve of the FTF-ER method seen in Figure 4. The paper presents a novel approach to continual graph learning, introducing the feature-topology fusion-based experience replay, FTF-ER, method. This approach leverages Hodge decomposition to better understand the structure of graphs and improve the learning process. The FTF-ER method is designed to overcome catastrophic forgetting, a common issue in continual learning where the model forgets previously learned tasks as it learns new ones. The authors propose using a Hodge decomposition-based feature fusion strategy to combine node features and topological information. This fusion strategy helps in identifying and preserving essential information from previous tasks, thereby reducing forgetting. The paper also introduces an experience replay mechanism that stores and samples experiences from past tasks to further enhance the learning process. The authors provide a comprehensive review of related work in the field, covering topics such as graph neural networks, Hodge decomposition, and continual learning. They also detail the mathematical concepts and algorithms used in their approach, including the Hodge decomposition theorem and its application to graphs. The FTF-ER method is evaluated on various benchmark tasks, demonstrating its effectiveness in overcoming catastrophic forgetting and improving performance on subsequent tasks. The paper concludes by discussing the potential applications of this approach in real-world scenarios and highlighting future research directions. Overall, the paper presents a significant contribution to the field of continual graph learning, offering a novel solution to the problem of catastrophic forgetting. The use of Hodge decomposition and experience replay mechanisms provides a robust framework for learning and preserving knowledge across tasks, making it an important read for researchers and practitioners working in this area. In the realm of machine learning and artificial intelligence, the Hodge decomposition theorem on graphs provides a powerful tool for analyzing graph-structured data. This theorem decomposes a graph signal into three orthogonal components: gradient, curl, and harmonic. The gradient component represents the conservative or curl-free part of the graph signal, the curl component represents the rotational or divergence-free part, and the harmonic component is the part of the signal that is both gradient-free and divergence-free. To apply this theorem, one must first define certain mathematical operators such as the gradient operator, negative divergence operator, and graph Laplacian operator. These operators are used to compute the topological importance of nodes in a graph. The graph Laplacian operator, in particular, corresponds to the usual graph Laplacian operator, which is a fundamental concept in graph theory. The Hodge decomposition theorem on graphs has applications in signal processing, data analysis, and machine learning on graph-structured data. It provides a way to analyze and understand the different aspects of a signal's behavior on a graph, including conservative, rotational, and harmonic components. In addition to the theoretical aspects, experimental results are also presented to demonstrate the effectiveness of the node representations learned by the FTF-ER method. A qualitative analysis on the Amazon Computers dataset shows that FTF-ER exhibits a clearer separation of nodes from distinct communities compared to alternative methods. This showcases the capability of FTF-ER in capturing distinctions among nodes within diverse communities through the gathered node information. Furthermore, the sensitivity of the hyperparameter beta is analyzed, demonstrating its different effects on various datasets. The peak consistently occurs at the middle position on all datasets, further confirming the effectiveness of the feature-topology fusion sampling. Overall, the Hodge decomposition theorem on graphs offers a valuable framework for understanding and analyzing graph-structured data, and its applications in machine learning and artificial intelligence continue to grow.